Okay, thank you. Thank you for the invitation, and I will talk a bit about Kaon physics in my talk with an experimental angle. But first of all, I just want to have a quick introduction to set the scene. So it's in this 2 weeks of the school and then the workshop, you've heard many times, obviously, that we're all looking for new physics, and basically Kaon decays are, I mean, from the Feynman diagram point of view, loops, and loops are sensitive to the presence of new physics. So in general, rare processes can, it's a place where new interactions can give a contribution and therefore cause deviations from the standard model. Also, new interaction can have a different symmetry. And the point that I want to make is that basically over-constraining the new interaction, so in the beauty and the charm that you've seen a lot in this series of lectures, but also in the strange sector, is in fact crucial to understand the origin of new physics. In particular, there are sort of two strategies that experimentalists follow. One is, of course, search for deviation with respect to standard model prediction. But here, clearly, one has to look specifically or particularly for those processes which are sensitive to contribution of beyond the standard model, of course, but also accessibly experimentally and without big hadronic corrections or hadronic uncertainties. This is somehow the ideal place. And some specific flavor changing neutral current processes are of this kind, and I will show you in Kaon physics what they are. The other way is search for really forbidden processes in the standard model. For example, this is a lepton flavor violation or lepton number violation are examples, and these are generally clean probes of new physics. So if you see something, that is definitely new physics. And again, I will show some examples in Kaon physics in this talk. So just to put this in the Kaon context a little bit more, there are a series of flavor-changing neutral current processes which are dominated by short distance contribution, but what dominated means it changed to some extent. So for example, here there is a table where you see at the top, there is K long to mu plus mu minus, where the short distance contribution with respect to the total width is 10%. And so the still suffer from quite a bit of a contribution from long distance. And so if we go down that list, in fact, we get to more and more short distance dominated processes. And at the bottom, the two lines is the pi charge or neutral, the pi nu bar decay, which is largely, as you see, dominated by short distance contribution. Now, the unreducible theory error, so basically really the fundamental error of the calculation is of the order of few percent. Now, however, the standard model Branchy ratio predictions also has inputs from CKM elements, and therefore, at the moment, the uncertainty on the standard model prediction, all considered, is it's around 12%, 10–12%. And so then the basically, as you see, also that you can have unitary triangles in, of course, in the B sector. You've seen it a bit in these lectures, I'm sure, but also in the Kaon sector. And so that is the triangle in the Kaon sector with the noticeable decays on the various axes. So you see that, for example, the K long to pi 0 nu bar constrained the height of the triangle, where the pi plus constrained one side of the triangle. And so in general, if one managed to measure all the charge and neutral Kaon mode, then we can over-constrain the triangle in the same way it's done in B physics. So now the golden channel Here, as you see as you saw from the table before, is the pi nu bar, which is flavor changing flavor neutral current processes, as you see from this box and penguin diagrams. In fact, those are the highest CKM suppression, order lambda to the 5. And the important point here, that's why they are so called golden, is that the hadronic matrix element is related to a measured quantity, and therefore they benefit from an exceptional precision of the standard model prediction. Is basically free from hadronic uncertainties. However, from the pie chart at the top of the page, you see that the theoretical uncertainty contains a lot of contribution from CKM element. But basically, this is theoretically very clean and sensitive to new physics, to high mass scale that are in principle of the order of 100 TeV, so very high. So then one can also rearrange the prediction of the Branchy ratio for the pi nu as a function of the CKM elements explicitly. And here you see that there are sort of a bulk contribution that factorize out. And then there is a dependence on CKM elements and the angle gamma. And so, in fact, the dominant uncertainties are from CKM elements, and here it's very explicitly seen, while the theory uncertainty, the intrinsic theory uncertainty, is very small. And so again, here you see the unitary triangle on the plot and some hypothetical CKM fit with a high precision, 10% precision, basically for K plus and K long. And so you see that somehow this is, as soon as the experimental uncertainty shrinks, then indeed one can reach sensitivity complementary to the B decays and constraint for new physics. Now, the new physics models have different impact on the K long versus K plus. And so on the horizontal scale, there is a K plus, and on the vertical, the K long. There is also this gray bound, which is the normal green Grossman near bound, which is basically a ratio, Branchy ratio in a lifetime. And the various models are here in blue, in red, and in green. So essentially, the green are minimum flavor violation models. So basically, where the flavor structure is like the CKM. The blue are models with a new flavor violation interacting, but with specific model and specific constraints. And the red one is just generic model without the above constraints. And so you see that the correlation between the two, the charge mode and the neutral mode, is very different depending on which model we are talking about. And so in general, constraining more than one Kaon decays is essential, is very important to see which type of new physics model we are going to constrain. As an example, I also have a plot here of the Lepton flavor universality violation correlation between a B channel, so B to K plus nu bar, versus K plus to pi plus nu bar. So the analogous channels in the Kaon and the B sector. And indeed, there is a correlation. And this is a general thing that also is true for other B decays versus K decays, that in new physics models, because you'll have to establish what flavor structure the new physics has, then you can have different correlations between the K sector and the B sector. So testing all sectors in the flavor, it's important. So then I'm going to show in the next the status of the golden channels investigations. So the first experiment is the NA62 experiment at CERN. And here, the beam is 400 GeV protons from the SPS with a long spell of about 3 seconds spill. So the beam arrives in a 3 seconds chunk of time every about 15 seconds or so. So it's a 75 GeV momentum, really quite precisely. But it is an unseparated hadron beam. So essentially, it's just protons on a beryllium target that then produce all the hadrons. And therefore, it's not a Kaon beam. So the Kaons are only something like 5–6% of the beam. So therefore, one needs to decide if the particle in the beam is a K or a pi. And so there is the first decay in the beam line is the K tag, which is a Cherenkov and is a differential Cherenkov. So it can isolate pion and kaons precisely. And so that will tag the particle in the beam of either a pion or a kaon. Then one needs to measure the momentum and the position of the beam particle. And for that, we have the GTK. So the Giga tracker is called Giga because the rate in the Giga tracker is about 1 gigahertz of beam. And so it's able to track every particle in the beam and show position and measure the momentum because it's inserted in an achromat. Although in this view looks straight, but is in fact in an achromat in the other projection. Then there is a veto, in fact, nowadays a set of vetos at the start of the fiducial volume. And then the fiducial volume opens up. This is the vacuum tank that you see there, and is instrumented with large angle vetos that should help removing any decays that is not what we want to observe. And then there is a set of straw trackers in vacuum to measure the momentum and the direction of the decay particles. Then the rest of the detector is to measure the energy of the decay particle and to identify what type of particle they are. And so, for example, there is a rich to identify the decay pions or muons from the kaons. There is calorimetry. So the main electromagnetic calorimeter is the liquid krypton calorimeter, but there is also small angle calorimeters and a muon identification system. So the experiment has taken data in 16, 17, and 18 at increasing beam intensity. The signal we want to measure is an incoming pion and an incoming kaon and an outgoing pion. And so what we can measure is the full momentum of the K and the full momentum of the pi. The two neutrinos are missing, and we are not able to detect the two neutrinos. So what we can constrain kinematically is the so-called missing mass squared. That is just the calculation with the full momentum of the K and the pi. So this is kinematically is basically what we have. The other important thing to notice is that, well, in Kaon decays, a particular very frequent decays is pi plus pi zero. And that the pi zero obviously produce 2 photons most of the times. And so one needs to be sure that the experiment, the detector, is very able to detect those photons because we want to reject pi plus pi zeros. And therefore, we need to put a cut on the energy of the pi plus to ensure that if the decay is pi plus pi zero, the rest of the energy that the pi zero will have is enough to ensure a very high efficiency in the detector. Okay, so that's the idea. Now, in the plot, you see the missing mass squared for the various components. The signal is in red and has been announced 10 order of magnitude, and the rest are all background. So then you see immediately that there isn't a particular place where there is only signal. But there is instead a huge peak since this, the vertical scale is logarithmic, so there is a huge peak of pi plus pi 0. And so that forces us to define two signal regions on either side of the pi plus pi 0 peak to avoid the peak itself. And so in a moment, you will see our signal regions defined as region 1 and region 2 on the left and on the right of the pi plus pi 0 peak. Okay, so then the reduction of the background is based on particle ID, on timing between the detectors, because the K and the pi needs to be aligned very well in time. And basically that's it. The vetoes all around, and at the end of the detector, the particle ID that identify the pion and suppress the rest, the muon and the electrons, and a very, very specific time constraint between the K and the pi. And so in the 2016-17, we had in 2016 data of 1 candidate and 17 2 candidates. And here you see the missing mass versus momentum of the pion. And in the box, the red boxes are signal region 1 and 2. And outside there is the various other decays. In fact, the basically almost horizontal line, that is the contribution of pi plus pi zeros. That's the peak that we needed to eliminate and force us to have two signal regions separated. At the top, you see a sort of a blob, and those are decays to 3 pions, to 3 charge pions. And at the bottom, you see a sort of, a band, and that band is decay to muon neutrinos. So those are the main decay from the counts that we can obviously see very well. And then analysis, which I will highlight in a moment, allow us to sort of separate the main background from the signal. So in 16 and 17, we had a limit, of course, because it's only 3 candidates. And then in 2018, we had a lot bigger sample, and also we re-optimized the analysis. And so I'm going to show you that we inserted a new collimator before the fiducial volume. And so then allow us to re-optimize the analysis and also extend the signal region in a little bit bigger momentum range for the pi plus. And so here you see as a sketch that what we've done, we still have the 3 main region of background, the 3 pi plus pi 0 and mu nu, but we also define control regions and of course, as well as the signal regions, which are here blinded. And so the control regions are somehow sandwiched between the background region and the signal region and allow us to make the first estimate of the background in the control region and validate what we see with our estimate before opening the blind regions, and so opening the box. Okay, so for the background evaluation, this is our result. And basically, we always use data from control samples to evaluate the background because the signal, it's basically 10 to the minus 10, and it's very hard to be sure that you have a Monte Carlo, very good to all that down to those order of magnitude. And so if possible, we use data from control samples to evaluate our background. And you see here that there is a very good agreement between the predictions and what we observe in the control region of the background. That's the plot that we have there. And so it's a really good agreement, which is reassuring. And so we have an expectation for the background for the 2018 analysis, which is the one highlighted here. And you see that the main contribution in the signal region from Kaon decays is in fact the pi plus pi 0, because I'll show you in a moment that there are tails in the distributions. which makes it somehow overflow to the signal region. But there is also something called upstream. And so those are Kaon decays that happens, in fact, upstream of the fiducial volume that are not entirely vetoed by our system of vetoes. So in fact, for the per plus by zero is a general idea that you have the per plus by zero region here in red. And so you count how many events you have with the selection. And then you have a way to know an extrapolation factor that takes you from the background region to the control regions and then to the signal regions. And this sort of extrapolation factor can be determined looking at the control data and looking at the tail of the distribution. For example, for per plus by zero here in the missing mass squared, the tails of the distribution of this in the control regions. So the background is completely data-driven, with one exception, which is the pi e nu, because there isn't enough in the data, so we use the Monte Carlo. However, we validate the Monte Carlo and the expectations and the data in the missing mass squares. You see there is a very good agreement. And then we invert a set of cuts to enhance the sample, and then we can then calculate our prediction in the signal region. So what is the upstream background about? So before 2018, we had an old collimator, what we call old collimator, which, as you see, so the beam pipe is the little thing, very little thing in the middle, the red box. But as you see, we could observe a huge amount of events passing through, in fact, jumping up the collimator. If you see, the collimator is small. And so things could decay upstream, get out of the beam pipe, and somehow pass through the collimator on up and below. So then in 2018, that was replaced with a lot bigger collimator, as you can see. So then it's a lot harder for particle to then try to jump the collimator up and below. And perhaps this is better seen in this sketch, where if you have, for example, a decay in the achromat of the GTK, which is this ginkane that you see here, a decay of the Kaon in, for example, with two photons, then the pi plus, could jump and come in the decay volume originally, but then with the collimator, it can happily die in the collimator and so not be seen. So the upstream event rejection, we then did it in 2018 with BDT, so a boost decision 3, and that was possible just because of the installation of the collimator that cleaned the sample. And so we do a K-pi matching and geometrical variables in our BDT, and we train the BDT on the signal sample with the Monte Carlo and on the background on the data, and then we put a cut on the BDT. And then again, we invert the cuts on the K-pi matching to enrich the sample and be able to check in the control regions that we understand the background. And so, for example, the CDA, the distance of closest approach between the K and the pi is one example. And here in the plot, you see that the background data and model corresponds, matches very well. And this is very different from the distribution of the decay of the Kaons, the true Kaons that you see in gray. Okay, so then the other point is that in Na62, we don't have the idea of luminosity, like in the collider talk that you saw. But what we need to know is the amount of Kaons that we collect in the experiment. So to do so, we looked at how many known Kaon decays we have. And so we looked, in this case, to per plus by zeros. Then I mean, this is so-called our normalization. It's the equivalent of the luminosity, basically, that tell us how many Kaon decays there are in the experiment. And so we do this selection for pi+pi0 as our normalization, but in doing so, we also know that when it comes to pi plus nu bar, there are some differences, and so we have to correct for differences in the acceptance, in the trigger efficiency, and we also have to correct for one thing that is called the random veto. Because the pi plus in the signal decay is only one pi plus, we have cuts on accidental activity or pileup, as we want to call it. But this also causes a signal loss, because you can have an accidental signal that just come in the same time as a signal, and you cut it away just because it's at the same time window, but it's basically causes a loss of the signal. So the so-called random veto as a function of intensity is obvious, I mean, getting worse. And there is something that we measure, and this is this plot at the bottom. So we take into account that. Okay, so then for the data that we have, which is Run-1, this is our results. We find 20 candidates in total, with an expectation for the standard model of 10 and a background of 7. And that gives us a measurement of the Branchy ratio at 3.4 sigma significance. And so if we put this in context historically, you see that it's going down, the prediction of the theory is shrinking very much over the decades. And the experiments are also, the precision are also very much approaching the prediction now at fast rate. And so at the moment, the Na62 is the most precise determination of this decay rate and the strongest evidence of its existence at 3.4 sigma. And if you see the parameter space of K long versus K plus and the standard model as a cross, Na62 Run-1 has already excluded part of the phase space, but clearly we need a better precision to get closer to the standard model. So far, again, in the sort of new physics plot that I showed before, this is what Na62 Run-1 does in terms of excluding the parameter space. Clearly, one would like to have better precision, and so the idea is that Na62 has been approved to run for Run-2, which is up to 2025 of the long shutdown 3, as we call it at CERN, to reach of the order of 10% precision, which would cause a shrinking of the space in this new physics generic space as shown in the plot, and would help us also enhance our sensitivity to other rare Kaon decays. So what we've done for the next data taking that is starting, in fact, it started last year for Run-2, is that we added the 4th station of the GDK. We also added the veto counter next to the collimator, and we added the second calorimeter at the end of the beamline, the so-called IISc. For muon rejection, we also add something called the anti-zero at the beginning of the fiducial volume. So this is the detectors, these added detectors are basically trying to reduce the background further, both the upstream background and the background for the dominant Kaon decay, which is pi plus pi 0. And so all the detectors were installed and commissioned in 2021. So we were very pleased, and also we managed to reach with a basically nominal beam intensity with an improvement on the trigger and data acquisition, and so that is very good. For the background, the rejection for the upstream, we put this veto counter here that essentially further constrains the opening of the final collimator, and so help us to identify the remaining of the decay that could pass through this time, not jump, but pass through this time the whole of the collimator and gets into the fiducial region. We also added the second IISc because some of the undecayed beam that goes through the beam pipe. That basically there is a beam pipe for the undecayed beam and through some detectors, for example, the rich. And it basically can have a photon interaction in the rich flange in there and produce E plus E minus that hence up undetected. And so if they are undetected, then the photon is undetected, and therefore that can mimic a background. And so we place the second ASP module to be sure that we detect them. So all of this is working and the analysis in progress. So now let's go to the Kato experiment that it's designed to detect K long to pi 0 nu bar. It's even harder than NA62 because this time you got 2 photons and nothing else. And specifically, you don't know where the photons come from because you don't have a charged particle to trace back. So, however, Kato has a projective calorimetry. And so you can reconstruct pretty much with the projection of where the photons comes through with some precision. And there is a pencil beam for the Kaon. So it's not a large beam spot, but it is really a pencil beam. And so you can do the same thing as NA62 does, basically doing a match, a kinematic match between the line of the Kaon and the line of the decaying particle. In this case, a pi 0, in NA62, a pi plus. And so here, the box is the reconstructed Z vertex versus the reconstructed pi 0 PT. And so the signal box is defined as you see. And then the question again is what background there are. And so the Kato experiment realized that there was a new source of background in a slightly similar way as we realized that we had the upstream background. And so the Kato has a background from the beam halo, K long, so K long going to gamma gamma, and also from the K plus in the generated when the K long hit the collimator. The last collimator. And so that, for example, can go to K plus to an E plus that is not detected, and then 2 photons that are detected. And so the Kato experiment had a limit of the sensitivity of the order of 10 to the minus 9 with the 2015 data. And then with the 16 to 18 data, 3 events appeared. With sensitivity of 7, 10 to the minus 10, with so the 3 events with 1.22 background events. So that again places an upper limit of 4.9, 10 to the minus 9, and 90% confidence level. So this is where we are. And for the prospects, in 21 and 22, there is a shutdown to do the upgrade of the beamline, and an upgrade also the data acquisition of Kato that should be able then to deal with 4 times more flux than what we had so far. And so in 2022 to 2025, which is the next data taking of Kato, the aim is to reach the standard model sensitivity of 10 to the minus 11 by 2026. Now, about other K plus analysis, so NA62 being designed for pi plus nu bar can also have managed to do various other investigations in the Kaon sector. And so the first one is that I'm going to show, they're all rather new, is a test of chiral perturbation theory in K plus to pi 0 E plus neutrino gamma. And this is our signal. As you see, it's a large signal, and using 2017 and 2018 data. And we define the variables Rj, which is the ratio of the Branchy ratio divided in bin of the momentum of the photon and the angle between the electron and the photon in the Kaon rest frame. And so we've measured the Branchy ratio in this bin, and there is in fact a tension with the chiral perturbation theory predictions. But I mean, I cannot comment exactly on that or what implication these on the chiral perturbation theory discussions are ongoing. So then the other thing is a byproduct of pi plus nu bar. One can treat it as, in fact, a standard model background to search for x, an hypothetical k plus 2 pi plus x, where x is a scalar or a pseudoscalar. And because we have to know the background quite well for the pi plus nu bar searches, then we can also perform the searches for this exotic particle x. And so here you see that assuming that this x decays only to visible standard model particle with a lifetime inversely proportional to the mixing parameter, we can put limits. Those are the curves in sort of orangey plus the line in purple. And also we can do an investigation of so basically having a limit of 1 sigma and 2 sigma of the branch ratio of the function of the particle mx. And we can do it as a function of lifetime. And so you see all the curves of exclusions in terms of the lifetime if this decays to visible standard model particles. And so in general, we have a good sensitivity, and we have improved these preview limits by about a factor of 4. And so we are working on it to try to improve our sensitivity in our sample further for Run-2. We also have precision measurements like, for example, k plus 2 pi plus mu minus. This is a Flavour change in neutral current decay again. And we have about 10 to the 4 candidates from Run-1, and we can measure the branch ratio. As you see, it's a very, very precise measurement at this point. We can also measure the form factors, A and B. And so the paper is in preparation, but you see that we can measure the A and B form factors and their correlation. And so this is a precise measurement. Now, the precision here is still is the most highest precision achieved so far, but is yet not sufficient to seriously challenge the standard model, and in particular the Flavour universality, because to do that, we also want to measure the E plus E minus channels, which is one goal that we would like to do in Run-2. Okay, so then in terms of lepton number and Flavour violation, there is also the possibilities to put limits on decays of the type K plus, for example, to pi plus, mu minus, E plus, or various other charge combination. All of this are blind analysis, and so you have a list of our limits achieved recently, and you see that in generally speaking, if you look at our plots, we have a very, very good control of the signal and background agreement, because the experiment has to do that way, because it's optimized for the pi-no analysis. And therefore, in a sense, these analyses are not for free, but are relatively easy to do, because we managed to have a beautiful agreement between data and Monte Carlo, and therefore then one can, with the dedicated right selection, but still this is possible, and then one just can look for these forbidden decays and put limits. And this is also another one, the K plus to pi minus, pi 0, E plus E minus, where we observe at the moment 0 candidate with basically negligible background observed. This is the first search at all for this mode, and the paper is in preparation. So basically, it's also in general, it's true that we can also look for heavy neutral lepton searches, where we look again for an excess of the data events over the estimated background, because as you saw, the background is determined and characterized very well. And so we had limits for the muon mode and the electron mode, and lately we also placed the limit to the K plus, 2 mu plus, and 3 neutrinos. And finally, this is an analysis that is a lot harder. It's the equivalent of the RK in the B sector. This is the RK of K plus to E plus neutrino divided mu plus neutrino. And the standard model this time is very precise again. And there is a previous measurement, but the idea is to reach a much, much better precision with a novel method using muon decays for normalization, which is a lot, basically it's a sample that is a lot similar to the signal and therefore reduces the systematic effects. And so we want to check, to do this very careful. This is a very precision measurement to the per mil level. And so the analysis is ongoing. So finally, NA62 can also run in damp mode, where the beam, rather than hitting a target, it goes to basically a dump, like a tax, and it's closed. The taxes are final beam defining element, but can be closed. And therefore, then the beam will hit there and possibly produce exotic, feebly interacting long-lived particles that then will go into the detector decay. And if the decay invisible object, then we can detect them. And so our damp mode is sensitive to forward processes, complementary to other possible designs of this kind of detector for this physics. But we are competitive, definitely, in the forward mode. And in fact, we collected about 10 to the 17 proton on target sample in 2021 and 2016 in Run-1. So this is the background of the Z vertex versus CDA in the case in which the feebly interacting particle decays into mu plus mu minus. And you see that in the Run-1, we had some background, which is all these red dots. But in 2021, we did refine muon beam. I mean, basically, we tune the beam magnets to sweep the muons rather than having them hitting the detector. They're swept away. And the beam halo, I mean, of the muons. And so we managed to reduce the background substantially. As you see, it's a background reduction of about 200, a factor of 200 between Run-1 and what will be in Run-2. So the analysis of the 10 to the 17 proton on target sample is ongoing. And now just a few words about beyond LS3. So there is the idea is to take advantage of an opportunity in the Kaon sector, which is going beyond the 10% measurement on pi plus nu bar, to approach the ultimate theory error of about a few percent. And here you see in the two scenarios that the 10% measurement with the current uncertainty on the standard model, including the CKM elements, I mean, it will be good of the order of 10%, but clearly we can do better. And if you look at the plot on the right, you see that then the standard model is the ultimate theory error. And then if one shrink the experimental uncertainty suitably, then there is really one have the very clear possible evidence of new physics. And so because in European strategy, the rare Kaon decays were in fact mentioned as one essential activity to do in particle physics, we are designing a broad program with multiple phases of K plus and K long beam and some period in damp mode to exploit the sensitivity of Kaon rare decays to new physics, in general with flavor changing neutral current processes again, but also with precision measurements and exotic particle searches. And so the idea is that the beam line has to be modified to stand at least 6 times the intensity. And then we can have the first step after LS3 in the K plus mode to basically approach the ultimate theory uncertainty, and then switch to the K long mode to do ultimately the pi zero nu bar, but also other decay searches before then. And so the idea will be to have a design of the experiment that is similar to NA62, benefit from what we've learned so far. But clearly, we need an improved time resolution to keep the random veto under control, and also to improve several other things like the low material budget, the photon efficiency, and so on. And so these, especially the timing requirement, is in synergy with the high luminosity LHC requirements for the detectors. And so we believe that this can actually be done conceptually in terms of the technology available. So also, for the K-long, one would have a lot of K-long decays in the fiducial volume. And so one intermediate objective that can be useful to study the new K-long beam before going to the very difficult decay pi0 nu bar would be to look at K-long to pi0 lepton plus lepton minus, so basically doing K-long with tracking. And also, one can look at lepton flavor violation in K-long decays and radiative K-long decays. So the idea is to start with the K plus, have an intermediate period of K-long beam with tracking, and then ultimately try to do the K-long to pi0 nu bar. Now, for the K-long to pi0 lepton plus lepton minus, this is famous channels that people has been trying to look at for quite a bit, has both short distance and long distance contributions. And in fact, the K-short, which NA48 has helped in seeing, can help reducing the theoretical uncertainties. The main background is unreducible. It comes from non-resonant decays with the gamma-gamma. But if the experiment can be designed with a sufficient resolution in the pi0 mass, then one can measure the signal above the unreducible background. So that's the basic idea. And then also for the damp mode, the physics goal would be to reach 10 to the 18 proton on target. And in fact, we are indeed basically complementary because we can see forward physics. We are complementary to other projects that have been proposed, for example, the shadow experiment and so on, that goes off axis. And so essentially what we can look, for example, is photons from neutral pion decays in the TACs and ALPS. That it's where we should be mostly sensitive. So the idea is to have an K plus phase, an experiment that is similar in design of NA62 with due changes, as I said, and for the K long is basically looking at the design of the Flavour experiment. Here we've foreseen the order of 10 to the 19 proton on target per year. And for the K long phase, there is the need to extend the hole backward because one needs to eliminate the lambda background. So it needs a certain optimization of the detector and the decay volume to do so. And that implies an extension of the basically of the cavern where the detector is by about 150 meters, which is one reason why this K-long phase at the moment is the last that we foresee, as well as being the most difficult experiment, in fact. So an LOI is in preparation. And now about Koto. Koto also has prospects, and so the Koto it's going for a Koto 2, which aim to achieve a standard model sensitivity of 10 to the minus 13 with more intense accelerator beam power, new beam line, and a larger detector to get better signal acceptance, but it will take basically 6 years to extend the Hadron Hall at JPark. And basically the aim is to have 35 standard model events with 56 background events. So the main idea is to extend both transversely and longitudinally the calorimeter diameter to enhance the fiduciary region and therefore enhance the acceptance for the signal and also to improve the veto system and the time resolution, because I mean, in a sense, the experimental issues, the cutoff phases are a parallel of what NA62 face. So I've been talking to you about the random veto, and Koto experiment has pretty much the same problem, and in fact, pretty much the same magnitude of the problem. And so they also need, for the next phase, a lot higher time resolution for their detector. And so in summary, the rare Kaon processes are an excellent portal to explore physics beyond the standard model. There are specific channels that benefits from high suppression and very clear theoretical predictions. But in general, a sort of a global picture is needed to pin down new physics. So one has to look at precision measurement, limits, and at discoveries to try to pin down the whole picture. And then we are basically designing plans both on both sides of the world, both at CERN and at JParc, to have a long-term high-intensity Kaon experiments. Thank you.
Thank you, Cristina, for this wonderful talk. Now the platform is open for a few questions. Can you please raise hands if you have any questions for Cristina?
So I just ask Sanjay. So yeah, thanks a lot, Cristina. I was wondering about, you were talking about these trigger efficiencies, and there was quite a large systematic uncertainty from those. So when you're looking at the future experiments, how are you going to get these under control to the level that you wish?
Yeah, so that's a very good question. Well, so at the moment, apart from the trigger efficiency, which actually for the Pioneer noise, it's rather good, but our trigger efficiency in the best modes are always, 98% to 99%. And still they give us some systematic. So besides, at the moment, they sort of limit what we can do in terms of the bandwidth. So when we go a higher intensity, in fact, we are thinking of moving, like LHC B, pretty much, moving everything offline.
Okay, so you'll adopt real-time analysis type things whereby you'll...
Yeah, yes.
Okay, so become, lossless, essentially, exactly, for your signals imagery.
Yes, it become lossless, and also somehow because it's a real time, it's on, then you can also do different things regarding addressing systematics. I mean, the trigger is such, the hardware trigger is such that either you take the event or they're lost forever. So it's a different attitude pretty much. Okay. But then, so we are testing this actually. At the moment, we have inherited the Felix system from Atlas, and so we are trialing on in parallel on a couple of detectors that we have, just to see how it goes.
Okay, so thank you. Thank you.
Thanks, Jim. Cristina, I have a couple of questions. You showed very earlier 2016 and 2018 data in earlier slides. Mm-hmm. And when you opened the box, there were a couple of events right on the boundary of the signal region. So how do you test that stability, like where to put that boundary? I mean, do you move around and see like whether how do you choose this one? It was right on the top of the
yes, so first of all, I must say that they are not so close to the boundary as they look like. So in the picture, it's true. They look like right on the boundary. But there are two things to say here, that the the dots are artificially big to be able to see them, obviously. So part of it is an unfortunate feature of the plot to try to make them visible. In particular, the resolution on the missing mass, it's very good. So they're not actually that close to the border in terms of resolution.
Mm-hmm. I see.
Yeah.
And I may have missed this detect the pion and Kaon propagation. So when before they hit the detector, is there a possibility that one of the you have 70% of the beam is made of pions and only 20%? Yeah. So is it a possibility that one of the pion from the beam or one or two can slip by and become your signal, or maybe not?
From the beam,
yeah.
Not well. I mean, so what they could do in principle is interact with the material. And then produce whatever, of which one pion enters the fiducial volume. So that is a possibility, but that's why we have this Chanti veto at the beginning of the fiducial volume. In fact, there is the GTK3 in that region, and the pions could interact in the GTK3, die there, and make a pion in the fiducial volume. And that's why we have the charge vetoes at the start of the fiducial volume to avoid that.
I see.
Now, but in a sense, the upstream background, which we are not successfully vetoed completely at present, in fact, enters in our background, is that it's slightly more complicated than that. So it's a weird occurrences, to be honest, but we are talking 10 to the minus 11. So, you know, I mean, only weird things happens. But you see, that's really quite weird, because the K plus decays, then the pi plus have just a really narrow thing to get through, right? Because the rest is vetoed.
Yeah.
Yeah.
Can I ask a quick question?
Yes, sure.
Okay, Cristina, excellent talk. I was just thinking, I saw a result before you spoke about lepton flavor violation. There was a slide wherein a 1999 result had only statistical errors. Is the reason because there were no systematics? It was negligible, or?
Where?
Just before your lepton flavor violation. Yeah, maybe a slide before this. No, not this one. There was a set where there was a 1999 result. It just caught my attention, but I didn't write the slide number.
Okay, in lepton flavor?
Before that, before you spoke about the topic, towards the end of your lecture, I mean, towards the end of the talk. Further ahead, maybe? Further ahead.
Further ahead, okay.
Yes, I think so. It's close to the end of the talk, maybe 10-15 minutes before. No, this is your summary, so no.
I don't know which, if you can, sorry.
Sorry, I didn't write the slide number. I mean, is it possible there were some results where I think systematic was not mentioned? Is it because it was negligible? Maybe later on you can check it.
It might be, or it might be that if it's dominated entirely by the statistics, then, you know, the systematics becomes less relevant, I guess.
Okay, that could have been. It was an old result, yeah, but the latest ones had.
Yeah, exactly, because then probably increasing the precision, then all the sources becomes relevant.
Okay, thank you, Cristina. Thanks.
Thanks, Seema. So thank you, Cristina. Jim, would you like to take it up from here?
Yeah, so thank you very much, Cristina. It's great to hear about all that's going on with the Kaon physics, and thanks to Sanjay for chairing the session. So we'll have a break now for a few hours, and our final two talks are starting at 4:45.